Now let's see each of the notations as a recap for the arithmetic progression in its general form. So generally the arithmetic progressions are denoted with a plus d, a plus 2d, a plus 3d, and this. This is the notation for an arithmetic progression in its general form, where this is the first term is denoted by a1, which is a, and the second term denoted by a2, which is a plus d, and so on, is what we get in each of its notation. And usually nth term of AP, which is generally called general term in its notation form, is given by an and with the formula a plus n minus 1 into d. So we generally denote the nth term with an, and it is called the general term of AP, which is given by the formula a plus n minus 1 into d. The other thing is that this is also called the last term if it is a finite arithmetic progression. For finite arithmetic progression, the last term is generally denoted with nth term, and it is generally denoted by L. The last term is L and given by am, which is a plus m minus 1d, is how we denote the last term. For finite, this is this, and this is how we identify each of the notations, where we have already discussed that a is always the first term and d is the common difference, and n is the number of terms, or it is the position of in arithmetic progression. So number of terms in arithmetic progression. So we need to know each of these notations in arithmetic progression when we do the problems, starting with the general form, each of the terms, and the last term denoted by this, and the nth term, which is called the general term, and the first term, common difference, and number of terms. So this forms the complete understanding of arithmetic progression in terms of respective notations. So now that we have seen the patterns connecting the arithmetic progression, now let's try to see the applications of arithmetic progression in real life. Generally, the word problems which are asked in exams are very much connected with real life situations. So in case of this, let's take one of the example real life problem where arithmetic progressions is realistically used out there. Say for example, I have a question which says, a stadium has the chairs arranged row-wise. Now there's a stadium where the chairs are arranged row-wise, every row, first row, second row, third row, etc., where the first row has 23 chairs, the second row with 21 chairs, third row with 19 chairs, and so on. Now the question here is, which row of the arrangement will have five chairs is the question. And the question here is, in the first row there are 23 chairs, in the second row there are 21 chairs, In the third row, it is 19 chairs getting reduced every row. And the question here is, which row of the arrangement will have finally 5 chairs exactly? So this question is purely an application of arithmetic progression. So let's see how we can use arithmetic progression connected to this real life situation of arranging of chairs in row-wise arrangement. So in case of this, I identify that a stadium has chairs arranged row-wise where my first row has 23 chairs in the first row, then comes the second row, then comes the third row, and finally I don't know which is the last row, which I denote with nth row because I don't know which is the last row. But here the nth row is the last row because we cannot have infinite number of rows. So this problem is an example of a finite arithmetic progression. So in my first row, there are 23 chairs. In my second row, there are 21 chairs. In my third row, there are 19 chairs. In my nth row, there are 5 chairs, which I don't know would be. So my nth row has, let me take this as nth row but not last row. So it has 5 chairs where I need to find the position. So indirectly the question is, which row of the arrangement will have 5 chairs? So I assume the nth row with 5 chairs, then I find the value of n. Is how I understand this problem mathematically connected to arithmetic progression. So the question here is very clear that in my first row there are 23 chairs, second row there are 21 chairs, in the third row there are 19 chairs. So in which row will I have 5 chairs? That is, I take this as nth term and I find n. So therefore, let's see if this is an arithmetic sequence. The first and foremost step is to identify the arithmetic progression of the given pattern. As I clearly see that the common difference of 21 and 23 is -2, and the common difference of this minus this is -2, and everywhere it is same. Therefore, this is an arithmetic progression with the common difference -2 fixed. So using the arithmetic progression concept, we will find the value of n. Now continued with the problem, the sequence is identified to be 23, 21, 19 and so on and so forth, where the first term a1 is nothing but the 23. A is 23 and the common difference d is nothing but the difference of 21 and 23, which is -2. So a is 23 and d is -2, and then my nth term is 5 because I don't know which row has 5 chairs, so I assume that to be nth row, and then I find the position n. So an is 5, which gives me the nth term, and therefore the nth term, when substituted with the formula, we know that an is a plus n minus 1 times d is equal to 5 using the formula for an. This, on further simplification, gives me, with substitution of a, which is 23 plus n minus 1 times d, which is -2, is equal to 5. So therefore, I substitute the values of a and d and then simplify so that I get this. This, on further simplification, gives me 23 minus 2 times of n, which is -2, and -2 times -1, minus into minus plus 2, which is equal to 5. Therefore, this, on simplification, gives me 23 plus 2 is 25 minus 2n equals 5. Now this, on further simplification, gives me minus 2n equals 5 minus 25, which gives me minus 2n equals 5 minus 25 is -20. So that minus gets cancelled and I get n equals 20/2, which is 2 ones, 2 tens, 10. Therefore, n is equal to 10. Therefore, when I convert this into the real life problem as asked in the given question, I understand that the 10th row will have 5 chairs in the stadium. Therefore, n equal to 2, 10 implies the 10th row of the arrangement will have 5 chairs in arrangement. Therefore, the 10th row of the arrangement will have exactly 5 chairs. This is how I understand the real life situation connected with arithmetic progression. Now let's see the next concept in arithmetic progression called the sum of first n terms of AP. But before we proceed with that concept of sum to n terms, let's come with an opening problem. Say for example, to start with the heading, sum to n terms of arithmetic progression. Say for example, on my 15th birthday, on my 12th birthday, my dad has given me the pocket money of rupees 1000. And from this 12th year, my dad has been practicing giving me a gift money every year on my birthday. So therefore, on my 12th birthday, my dad has given me 1000 rupees as the pocket money, which I have been putting in the money kitty money box. Similarly, on my next 13th birthday, my dad has given me 1500. So every time he was increasing 500 rupees as increment in the pocket money which I was receiving here. So similarly, when for the next birthday, on my 14th birthday, I was given 2000 rupees as the pocket money. So it was continuing until I reached up to, as my age was growing, my pocket money was increasing every time by 500 rupees every year. Then finally, on my 21st birthday, I was given some pocket money which I wanted to find. So this has helped me in identifying that this is an arithmetic sequence, because when I take them in with the common difference, I find that the common difference is same, and therefore this forms an arithmetic progression. Now I wanted to know what is the pocket money which I would be getting on my 21st birthday. Then how do I calculate the pocket money I get on my 21st birthday? Is nothing but finding the nth term. But not only that, I also want to find how much money I totally collected in my kitty box. I wanted to know by the end of my 21st birthday how much money I have in my money kitty box. So the question here is, how much money did I collect? So the question here is, how much money did I collect on the whole in my kitty box by the end of my 21st birthday? So I wanted to know the whole of the money which I collected from my 12th birthday, where the pocket money was started being given, which is 1000 rupees, and the next birthday where I got 1500 rupees, and the next birthday where I got 2000 rupees, so on and so forth, until I got my pocket money till my 21st birthday. So I wanted to know how much money did I get on the whole. So this question is quite different from the previous topic of n terms of arithmetic sequence, because we are finding the sum of all the terms of arithmetic sequence in this situational problem. So let's see how we can find the total money I collected in my kitty box by the end of 21st birthday. So therefore, if I wanted to find the 12th birthday where the amount I got is rupees 1000 and my 13th birthday where the amount I got is rupees 1500, then the 14th birthday where I got rupees 2000, and so on and so forth, I would like to find the total number of amount I collected by the end of the 21st birthday, where I don't know the amount and then I will first find the amount I collect on the 21st birthday and then finally up to this. So this can be done clearly by taking 12th birthday rupees 1000, 13th birthday rupees 1500, 14th birthday rupees 2000, and next 15th birthday is 2500, where each of 500 rupees is increased, so on and so forth until I reach 16th, which is 3000, and then coming to 17th birthday, which gives me 3500, then 18, 19, 20, 21. So to start with 18th, I get 4000, and 19th 4500, 20th is 5000, and finally my 21st birthday is 5500 totally. So that means on 21st birthday I get 5500, and each of the birthdays this is the amount I get, and then I wanted to find the total amount I get is calculated by adding each of them. Total amount I collect will be equal to each of the things added. So when I start adding 5000 plus 5500 is 10500 plus 14, 10 plus 14, 15,000, 15 plus 4, 19, 19 plus 3 is 20, 21, 22, 22 plus 6 is 28, 29, 30, 31, 32,500. So when I add each of this, and this, I get rupees 32,500, which I have collected on the whole when I collect each of the pocket money I got from my 12th birthday to the 21st birthday. By the end of when I open the kitty box, I see that I have totally 32,500, a good amount to buy a bike. Good, I can buy a bike with this, or I can buy a very good latest Android cell phone from this Sony Xperia. Now the 21st birthday problem which I have taken in the previous session may not be easy if I wanted to know the total amount I collect at the age of 99 or at the age of 87. If the value is big, then continuously adding up each of the pocket money I get on that respective year may not be an easy task. Therefore, if the numbers are very large, then random addition of all the terms of arithmetic progression is not possible. So let's find a derived formula through which we can find the sum to n terms of arithmetic progression for however large n is. Let's derive a formula. So in order to derive the formula, the credit goes to the mathematician Gauss, where he has invented a method of finding the sum to n terms of arithmetic progression using the Gauss method. So let's see the Gauss method of finding the sum to n terms of arithmetic progression. So in order to do that, let's consider the general arithmetic progression which we have already discussed in the previous sessions. So the general arithmetic progression here is identified to be a plus d, a plus 2d, so on and so forth. Finally, leading to the nth term a plus n minus 1 times d. So for this general arithmetic progression, a plus d, a plus 2d, and a plus n minus 1d, so on and so forth, I just take the sum because I need to find sum to n terms of arithmetic progression. Now these are the n terms of arithmetic progression. I sum up and denote with s. The sum s, when you add each of a plus d, a plus 2d, so on and so forth, is what we get when we sum up each of the terms up to nth term. Therefore, when I take s as sum of each of them, I would like to derive a formula for this. So in order to derive the formula for this, I take this as equation 1, and finally what I do is I retake s, but in the second case I arrange the terms from last to the first. I arrange from last to the first term. Therefore, my first term is a, therefore the last term becomes the first term out here. So I get a plus n minus 1d as the first term, and then the term before this being a plus n minus 2 times d will be the second term of the given second expression. Similarly, the third last term, that is a plus n minus 3d, will be the third term of this, so that finally I get the last term here as a, because the first term of this comes out as the last term, and then this is taken as equation 2. So this is how I arrange s in the reversing order of last term to the first term of equation 1. Then what I do is I just try to take these two equations and add them up, because let's see interestingly what happens when I add each of the sequences. On the left side, when I add, I get s plus s is 2s, and then when I add each of them, I take into consideration that I add this pair, and then I add this pair, and then I add this pair, respectively each of the pairs being added separately. Therefore, when I add this with this, I get 2a plus n minus 1 times d in case of this, and when I add this also I get 2a plus, this is the first term, and then I get 2a plus d plus n minus 2 of d, and then when I add this I get a plus 2d plus a plus n minus 3 times d, so on and so forth. I get a plus of this. This on further simplification gives me 2a plus n minus 1 times d, where this when simplified gives me 2a plus d plus nd minus 2d, which gives me minus d. So again I get 2a plus d minus 2d is minus d. So 2a, again I resimplify this, I get 2a plus n minus 1d, because when I take d common I get 1 plus n minus 2, which is n minus 1. Again this gives me a plus a, which is 2a, and this further taken in place gives me d common, n minus 3 plus 2 is again n minus 1. So therefore this also gives me an equal term, n minus 1d. So I observe here each of the terms when simplified gives me the same term, 2a plus n minus 1 into d, 2a plus n minus 1 into d, 2a plus n minus 1 into d, and so on and so forth. I get here 2a plus n minus 1 into d. So I get all equal terms until I reach to the last term, which are equal. Now I observe here there are n terms which are coming from here to here. There are totally n terms. Therefore, when I multiply 2a plus n minus 1 into d n times, I get 2a plus n minus 1 into d times of n, because since there are n terms. each of the term added n times gives me n times of the common term, since there are n terms. Therefore, I get here 2s is n times of 2a plus n minus 1 into d, so that my s is, when arranged, n by 2 into 2a plus n minus 1 times d, which is called the sum to n terms of the arithmetic sequence given by the formula. So this is how I understand the sum to n terms of arithmetic progression is given by n by 2 times 2a plus n minus 1 into d, is how we get the derived formula using the Gauss method. So this is the Gauss method of finding the sum to n terms of arithmetic progression using the reverse process, the derived formula out here. So the sum to n terms of AP, which I have generally derived here, is generally denoted with Sn or S, because Sn stands for the sum to n terms. If I say S5, it denotes sum to first 5 terms. If I say S3, sum of first 3 terms, etc. So the derived formula was n by 2 times 2a plus n minus 1 times d. But if I want to express this in the nth term form, then let's see how we can derive this into the nth term form. As I remodify this, I get here n by 2 times 2a. I can split it as a plus a, so that this can be written as it is down here. So this is split as a plus a. Next, I get this as a plus n minus 1 into d is identified to be the nth term an, which we already discussed, since here an is the nth term. An is the nth term of arithmetic progression. Therefore, also I have a as a1, because the first term a is generally denoted with a1 plus an is what I get for Sn. More in general words written as n by 2 times first term plus last term is how I derive the formula for sum to n terms. So if I'm given the first term and the last term, or the first term and the nth term, I can straight away use this formula as an extension of the previous derived formula. So this formula is exclusively used only when the first and last terms are given in the problem. Other than that, if my common difference in first term is given, I use this formula as derived in the previous case. So this is an extension of the derived formula. So let's see the notation for sum of first n terms. As we have derived the basic formula, let's recap in detail out here. So with the conclusion, we make that the sum of first n terms of arithmetic progression is generally denoted by Sn, is given by the formula n by 2 times of 2a plus n minus 1 into d, or it is also given by the formula Sn equals number of terms by 2 of first term plus the last term. So we can use either of them depending on the last term is given, I use this formula, or Sn is given, I use this formula, where each of the notations are given. We know that a is the first term, d is the common difference, n is the position or the number of terms of the given arithmetic progression, is how we derive for sum to n terms of AP. Now let's see some example problems supporting the derived formula. That is, say for example, I wanted to find the sum of first 7 terms of, say, the pattern is -1, 1/4, 3/2, and so on. Now, in case of this, I would like to find the sum of first 7 terms. So let's identify this to be, let's examine this for an arithmetic progression. So as I clearly see here, the pattern is -1, 1/4, 3/2, and so on and so forth. The common difference here is 1/4 plus 1, which is 5/4, and the common difference here is 3/2 minus 1/4, which on simplification gives 6 minus 1, which is 5/4. So this is an arithmetic progression because the common difference is same. This is an arithmetic progression. Now for this arithmetic progression, I wanted to find sum of first 7 terms, which is denoted by sum of first 7 terms is denoted by S7, and therefore we have the formula for Sn where n is equal to 7. So let's take the formula for Sn and then substitute n equal to 7. So as I already have, Sn equals n/2 times. Now here the last term is not given out here, therefore I don't take the second case of the formula, but since the first term and the common difference is given, I take the general formula 2a plus n minus 1 times t, where my n is 7. In this case, n is 7 and my a is the first term, which is -1, and my common difference is the difference of this term with this, which is 5/4. So substituting the values of n, a, and d in the Sn formula, I get the sum of first n terms, which is S7. So let's see how we can substitute each of them.